Let's work another example. We're going to return to this fourth degree polynomial function, this quartic that we worked with earlier. Now I've already put this quartic into my calculator. If I go to y equals, you can see I've got it stored in y1. You should go ahead, pause the video, put that into your calculator too so that you can follow along. Now we're going to approximate the x-coordinate of all inflection points to one decimal place. That's our goal here. That's what we couldn't quantify earlier. Now, on this slide, I've listed down here the local extreme points that we determined earlier for this function. So let's go to the graph, which, by the way, if we want to look at this graph on our calculator, let's go ahead and do that. I'm going to go to Window, and let's graph this. I can tell from this, what I'm looking at here on my screen, that I can go from about, let's say, -7 for x min and 12 for x max to recreate this high resolution graph on my calculator. So on the interval from -7 to 12, if I run zoom fit, we should see this picture on our calculator. And there it is. So from earlier, we found that the x-coordinate of this local minimum here is about -3.94. And the x-coordinate of the local maximum, right about here, is 0.79 on the x-axis. And the local maximum right here, which happens to also be the absolute maximum of this function, is at 8.33. So we know those points. And so roughly, look at this graph right here. We're from that first local maximum, we're decreasing at an increasing rate until we get to an inflection point, after which we're decreasing at a decreasing rate. There's an inflection point right about there. So that's going to be, it's definitely within the interval from -3.9 to 0.8. I know there's an inflection point in there. Now, after that, the graph is increasing at an increasing rate, and then at some point it changes to increasing at a decreasing rate. So there's an inflection point in here somewhere. That's going to be also an inflection point, and right into one decimal place, it's approximately between 0.8 and 8.3. So there's an inflection point in that interval. So I'm just using one decimal place precision on the endpoints to start, okay? And so now let's find those. Okay, so here's the work that we're going to be verifying right now. I've already just written it up here for you. Like I said, we know there's an inflection point in there from -3.9 to 0.8. So let's go to our stat editor and let's look at, we're going to break up that interval from -3.9 to 0.8 into subintervals of length 0.1. So I'm going to generate the x-coordinates that I'm interested in by pointing up to L1 and running sequence, which is under the list menu, operations. So select sequence, and the first argument is x, comma. Second argument is x, comma. The third argument is where the sequence starts, and that's -3.9, comma. The next argument is where the sequence ends, that's 0.8, comma. And then the last argument is the length of the intervals, 0.1. If you have the other interface, it's the exact same arguments in that order that you're filling in before you hit that paste command. So So I'm going to hit enter here, and that's going to generate the sequence. These are all the x coordinates that we're interested in. I'm going to move over to L2, and I'm going to point up to L2, and I'm going to generate the y coordinates for those inputs, the outputs that correspond to those inputs. So that's y1, where the function is, of L1, just like that. So these are the points. Now I'm going to calculate the average rates of change. You can go ahead and visualize this if you'd like I did on the last example, but now I've got the idea down. I'm going to look at these average rates of change. That's really what I need. I'm going to quantify the steepness on each of these intervals that we're talking about. So pointing up to L3, do delta list L2. Divided by delta list L1. Change in outputs divided by change in inputs. Those are slopes. Here are all the slopes. Now these are all negative, so I'm going to cursor down. I'm ignoring the negative sign. I'm looking at the magnitude. That's the steepness. And I'm finding then the largest magnitude. Keep cursoring down. Oh, we're now decreasing. So let's see. That's the largest magnitude. 2251 is the steepness on the interval from negative 1.9 to negative 1.8. That's what I've written right here. We now know that the inflection point is in that interval. So we're pretty close to 1 decimal place accuracy. We know to 1 decimal place the answer is going to be either negative 1.9 or negative 1.8. We have to break this interval up into smaller subintervals in order to figure out which of those endpoints the inflection point is closer to. So I'm going to clear. I'm going to go to memory, second memory. I'm going to clear all lists, just as a quick way to get rid of all of that information in the stat editor. Now I'm going to go back into the stat editor, and we're going to look at the interval from negative 1.9 to negative 1.8. I'm going to point up to L1, and I'm going to generate the x coordinates by using the sequence command. Under list, operations, it's sequence, x, comma, we're starting at negative 1.9, comma, we're ending at negative 1.8, comma, and we're incrementing by 0.01. We're splitting this up into intervals of length 0.01. Close the parenthesis, hit enter, and those are the x coordinates. Now I move over to L2 and generate the y coordinates of the points. So that's y1 of L1 using function notation. And there are the x coordinates. So now I've got a bunch of points on the graph. I'm going to calculate the average rates of change on adjacent points, neighboring points. I'm really calculating the average rates of change on intervals defined by neighboring points that I've plotted here, or that I've generated here. So pointing up to L3, delta list L2. That's the change in outputs, divided by delta list L1. Corresponding change in inputs. And here are those average rates of change. Now they look very close to one another, which we're looking at a very small overall interval. So I'm going to be looking, let's watch down here for these full precision answers. Let's see, did that go up? Yeah, that went up. You gotta read close, that went up, up. Oh, I think that went down. Let's see. 0.17621. 0.1, yeah. So that appears to be, I'm going to go up one more. Yeah, this is the largest value right here. That's the slope with the largest magnitude. We're ignoring the negative sign. The graph is decreasing here, and that's why these are all these average rates of change are negative. But we want the steepness. The steepness is 2251.18 roughly. And so now we're going to move over, and that's on the interval from negative 1.5 to negative 1.84, which is what I wrote right here on the slide. Now, any number within that interval, inside that interval, we're closer to, would be closer to the negative one. We're rounding to one decimal place. So anything within this interval is going to round to negative 1.8. And so the answer to one decimal place accuracy, that tells us the inflection point is at negative 1.8. Again, we almost have the inflection point to two decimal place accuracy. If we chose to continue on with this idea, we could split this interval into smaller subintervals, like with a delta of 0.001, and figure out whether we're closer to negative 1.85 or negative 1.84. But this is going to be good enough for us. The inflection point is at an x-coordinate of negative 1.8.